Welcome to Structural Engineering Online. In this video lecture, we will learn how to calculate support reactions of a simply supported beam. Please subscribe to our channel if you have not yet subscribed, so that in future you will get the notifications of new video lectures. Thank you. In this video lecture, we will learn how to calculate the support reactions for a simply supported beam with triangular load. Triangular load is also known as uniformly varying load. And in this lecture, we will discuss these three cases of triangular load. If you see here in case number 1, the maximum intensity of triangular load is at the midpoint of the beam. In case number 2, the maximum intensity of the triangular load is at one of the supports. And in case number 3, the maximum intensity is somewhere in between the two supports. So first of all, we will take case number 1, which is very simple. Case number 1 is like this. This is your beam with hinge and roller, and we have these reactions will be, suppose this is A, this is B, you will have two vertical reactions. We can say VA here and VB here. And as we have seen in the previous 3 lectures, that this horizontal reaction at A will be 0, right? Because there is no horizontal force. So first step in solving our problems for support reactions is that we apply the equations of equilibrium. So sigma Fy, we will start with sigma Fy equal to 0, because sigma Fx equal to 0 has already given you this Ha equal to 0. So there is no need of repeat that. If you want to see, you can see our previous lectures for support reactions, lecture 1, lecture 2, lecture 3. Okay, sigma Fy equal to 0. So in that case, we have the reactions at the supports which are vertical. So these are the two reactions. So we have here plus VA plus VB, and then this triangular load. So how we calculate this total triangular load? It will be just equal to the area of this triangle. So area of the triangle, as you know, the formula is area half base into height. So base is 4 and height of this triangle is 2. So we can simply say, and this is acting downward, so that will be the total load, minus half into base, which is 4, and the height is 2, and this whole thing equal to 0. This is our sigma Fy equal to 0. Algebraic sum of all the forces in y direction equal to 0. Okay. From here, when we simplify this, we get plus VA plus VB, and this will be equal to 4. This is our first relationship. Okay, VA plus VB equal to 4. Okay, then we apply second equation, sigma m. Okay, we take moment about A, and this gives what? VB into 4. Okay, so we write here VB into 4, and this will be anti-clockwise, so we have plus VB into 4. VA and HA are passing through the same point A, so they will not give any moment. Now we take the moment of this triangular load. As you know that the total triangular load is equal to that area, which we have already calculated. But where it will be acting, because in the case of moment, we must know the point of application of that load. In the case of this symmetric triangle, it will be acting at this halfway. That means at a distance 2. So this will be its center of gravity, will be passing through this. So centroid, or you can say that the reaction, the resultant of this triangular loading will be at the midpoint. So we can say that VB into 4 minus this total load, which is half into base, which is 4, into the height, which is 2. So this is load. Now the load multiplied by the distance of its centroid from the point of moment, which is equal to 2. So this whole thing will be equal to 0. From here we can say, okay, this will be equal to 8. So VB into 4 will be equal to 8. Therefore, VB will be equal to 8 upon 4, that is equal to 2 kilonewton. Once we get the value of VB, we can easily calculate VA. Therefore, VA equal to 4 minus 2 equal to 2 kilonewton. So we found that when the loading is symmetric, the two reactions will be equal. So total load divided by 2 will be the reaction at the support. So this is very simple case. And now we come to case number 2, in which the maximum intensity is at one of the supports. Okay, we draw the diagram. So case number 2, here is this beam, maximum at, okay, here is hinge support, we have roller support, the intensities here 2 kilonewton per meter, and the length, okay, we take same length 4. This is the beam span L. Okay, this is your point A, this is B, these are the two supports. Now in the similar way we will apply our equations of equilibrium, because we will have these two reactions, vertical and one horizontal reaction, HA, VA, VB. And we have seen in all our previous lectures, because there is no horizontal loading, so for maintaining the equilibrium in x direction, our HA will be equal to 0. So of course we apply the equations of equilibrium, which are sigma fx equal to 0, and that gives you HA equal to 0. This we have seen in our previous lectures also. So now we start with second equation, sigma fy equal to 0. And when we apply this sigma phi equal to 0, we get that VA, which is acting in the upward direction, VB also acting in the upward direction. So we get this plus VA plus VB. This is uniformly varying load, which we call as UVL. This is equal to same total area of this triangle, and that is same half base into height. So we say half base is 4 and the height is 2, and this whole thing equal to 0. So from here we can say, okay, VA plus VB is equal to 4, equal to the total load. Then we take the moment of these forces, that is third equation of equilibrium, sigma ma equal to 0. And what we get from here, we take moment of VB about A, and that will be anti-clockwise, so positive VB into 4. Now the moment of this triangular load. For taking the moment of the triangular load, we should know the point at which this load will have its centroid. So the centroid will be passing through a point which is at a distance. If you see, you can keep this in your mind here. For any triangle, the centroid will be, if this is the base B and this is height of the triangle, it will be at a distance of 2b by 3 from 0 value, and from this side it will be b by 3 from the height. Okay, so this is, you can say, the resultant of this triangular loading. So now in this case we have Vb into 4, which is the moment of Vb, and now we take this, the moment of this triangular load, which will be giving you clockwise moment. Okay, so we take Vb into 4 and then minus half into 4 into 2. This is your triangular load, and where it is acting at a distance of 2b by 3. Now the base is how much? Base is 4, so into 2/3 of base, which is 4, and then divide by 3. So this is the distance of centroid of this triangle, and this whole thing equal to 0. Okay, now we can simplify this. We can say, okay, this is 4 Vb, and here to 4 into 2, 32 by 3 equal to 0, right? 32 by 3, and then we can calculate the value of Vb from here, which is equal to 32 by 3, and then 4 comes here, so it will be 8 by 3 kilonewton. So this way you have got the value of this reaction at B. Once you get the value of Vb, you can easily calculate Va. So therefore Va is equal to 4 minus the value of Vb, because Va plus Vb is 4. So we substitute the value of Vb in that equation. So 4 minus 8 by 3, which is equal to 12 minus 8 by 3, and that is equal to 4 by 3. So in this way we have got the reactions when the triangular load has maximum intensity at the supports. Now here I will tell you one simple rule also, that when you have this type of loading that the maximum intensity is at one of the supports, and you can see here that this is 4 by 3. This is just the total load divided by 3. If we have total load W, it is just W by 3, and this reaction Vb is nothing but 2W by 3, right? This is 2 into 4 by 3, so it is 2W by 3, where W is your total load, which is half into base, which is your 4, and the height is 2. So W is 4. So this way it is very simple for you to calculate. Wherever you have the maximum intensity of this triangular loading, you will get 2/3 of the total load, and on the other support where intensity is 0, you will get 1/3 of the total load as the reaction. Okay, now we go to the third case. In this case we have somewhere like this, where this is maximum somewhere between the two supports. So if we say this is hinge and this is roller, and the maximum intensity is somewhere in between. We can say that this distance is 3 and this is 2 meter, right? This is support A and this is support B. The intensity is same, 2 kilonewton per meter. Okay, so we'll solve it in the similar way. First of all, the reactions. Okay, we'll show the possible reactions here vertical, VA, VB, and then horizontal, because hinge support will have two reactions. Okay, we can say HA, VA, VB like this. So HA will be equal to 0 by the same argument, because sigma Fx is one of the equation of equilibrium, and to maintain the equilibrium in x direction, HA will be equal to 0. Then our second equation of equilibrium, sigma Fy equal to 0, and this will give you plus VA plus VB, and now the total load of this triangle. So triangular load, again we will calculate in the similar way, that it is equal to the area of this triangular load diagram, and it is acting downwards. So downward forces we are taking as negative, upward positive. So we take here minus half base into height, the same what we have done previously. So base in this case is 4 and the height is 2. This whole thing equal to 0. So from here we can say that VA plus VB is equal to 5, which is the total load of this triangle, right? Now the third equation, sigma M about A equal to 0. And in this case we will take the moment, but we will not take the moment of this whole triangle at a time. We can easily solve this problem by dividing this triangle into two parts, and you can see that one triangle I can take like this, and another triangle I can take here, the second triangle. So we divide it into two triangles, one triangle having the base of 3 and the other triangle which is having a base of 2. So both these triangles will be separately considered, because we know the position of centroid for these triangles. So in this case, if you look here we have this triangle number 1 on this side, and I take this small triangle as triangle number 2. So we already know that if this is your base, then this centroid will be 2b by 3 and this distance will be b by 3. Similarly, if this is your triangle, and in that case this is your base b, so that distance will be b by 3 and this will be 2b by 3. So like this we will be taking the moment of these loads. So we have here VB into 5, the moment of VB, which will be clockwise, and then we take the moment of this triangle number 1. So triangular load here is same as half base into height. Now base for this triangle number 1 is 3 and the height is 2. So this is the load. Now the moment of this load, because its centroid will be at a distance of 2/3 of its base. So from A, that distance will be 2/3 of 3, because the base of this triangle is 3. Then we take the moment of this small triangle here, the small triangle, that is triangle number 2, and it has the area half, base is 2 and the height is 2. So this is the load. But we have to multiply the load with the distance of its centroid from A. So in that case, this is your centroid, right, which is 1/3 of 2, and that distance you have to measure from A. So we can say that this is 3 plus 1/3 of 2. So 3 plus 1/3 of 2, and this whole thing will be equal to 0. So what we get from here, we get 5 VB, and then we can say, okay, this is 3 into 2, which is 6, and then here also we can say that this is minus 2 into 11 by 3 equal to 0. Okay, so from here we can easily get the value of VB. So we can say that 5 VB is equal to 6 plus 22 by 3, which can be 18 plus 22, that is 40. So we can say here that 5 VB is equal to 40 by 3. Okay, so we get VB as 40 divided by 15, or 8 by 3. Once we get the value of VB, we can calculate VA. So VA is equal to total load. VA plus VB was 5. So when we substitute the value in this equation, we get the value of VA, that is 5 minus 8 by 3, and that will be 17 minus 8, sorry, 15 minus 8, that is 7 by 3. So this way we have got these reactions. So VB is 8 by 3, VA is 7 by 3. So in these three cases of triangular loading, now you know how to calculate the reactions for your simply supported beam. So I hope this helped you in learning the calculation process for support reactions of simply supported beam when there is triangular load, case number 1, case number 2, and case number 3. So if you like this video lecture, please share it with your friends, and also subscribe to our channel. In future we will also be uploading some more video lectures, so please continue watching our channel. Thank you very much.